Okay, let's get started. If you haven't turned your quiz 2 in, there's diminishing time until you can turn in your quiz 2. And make sure to pick up your quiz 1, whoever's left. Everyone turn in your quiz 2? Okay, cool, thanks. So I'll grade those by Friday, hopefully. Okay, so any questions since last time? So I posted homework 1. It's due a week from today. So any questions about homework 1? Okay, cool. So let's continue where we left off. So last time we were talking about these regular operations on languages. So what are those regular operations that we talked about? Union's one of them. What are the other ones? Concatenation, and what was the last one? The cleaning star, yeah. We'll probably just call it star for now, from now on. But okay, so we were focused on union last time, and I claimed that, without proof, that if we have two regular languages, their union is also regular. That's what we wanted to show. So what does that statement really mean? What would we have to do? So if L1 and L2 are regular languages, what do we know about them? They have a DFA for them. So if I want to show that L1 union L2 is also regular, what do I have to show for it? There's a DFA for it, okay? So I have two DFAs right here that we did last time. So I have a little machine Q0, Q1, and I have another little machine R0, R1. So the idea of just run one machine and then run the other machine didn't work because you can't resurrect the input once you have read it. So yeah, go ahead.
Why exactly is that?
Because that's just the model that we're working with. We will eventually work with a model where you can go backward through the input. And it turns out that if you modify the definition of DFA to allow it to go backwards and forwards on the input, as long as you don't modify it, you still get regular languages. But that's a much harder thing to do. It's much easier to focus on just going through the input and never being able to go back. It's just easier that way. But yeah, there are other models that allow for that. Okay, so here, what can we do? Well, the idea that we started to talk about last time was I have the Q machine in one half of my brain and the R machine in the other half of my brain. And then I think, okay, I'm at the beginning of both machines, which is in Q0, R0. And then what do we do on input 0? Well, I look on the first machine, see what it did, and look on the second machine, see what it did, and I update both halves of my brain simultaneously. Okay, so let's just say that we are in Q0, R0. If I read a 0 in both machines, well, what did both machines do? What does the Q machine do on input 0 from Q0? It goes to Q1. Okay, good. What does the R machine do? It goes to R1. Cool. So in my brain, I'm going to say the Q machine is now in Q1 and the R machine is in now R1. And then as we read more characters, I just update both of the states at the same time as we read more of the input. So let's think about this though. Could we conceivably be in R0 and Q1 at the same time? I'm just saying, is it conceivable? Yeah, it's conceivable. Could it be R1 and Q0, again, also. So what we can do is, let's look at all 4 of those possibilities. Because there's 2 choices of states from the first machine, and 2 choices of states from the... Sometimes it happens that it thinks I said, hey, Siri, but okay. So there are 4 choices of states here. So we noted this last time by ordered pairs of states. So I'm going to have a state called Q0, R0. Maybe I'll change the color of this. Oops. Can I select? I guess not. I guess not. Okay. So then I'll have a state Q0R1, Q1R0, and Q1R1. Because there's 4 possible choices of what could happen. I can be in 2 states of the first machine and 2 states of the second machine. Independently, I could be in all 4 combinations. So of this 4-state machine we're building, which state should be the start state? Q0, R0, because that's where both of the original machines started. So I'm going to make that guy the start state. Okay. I actually flip-flopped the order of the states that I wanted to do, but okay, let's just go with this anyway. Okay, Q0, R0. Well, we noted that on input 0, that took us to Q1 and R1. So I'm going to make a transition from that state to the Q1, R1 state on 0. We're just keeping track of where the original machines went. What about on input 1 from that same state? Where does the Q machine go? It goes to Q1 also. What about the R machine? Goes to R0. Good. So it's Q1, R0. So I'm going to write that. Okay, so now we handled that top left state. Let's do the Q0R1 state in the top right. So where does that go on input 0? Well, again, we have to look at what each of the machines would have done. On input 0 from Q0, where does that take us? It goes to Q1, good. So in our brain, we're thinking Q1. From R1 on input 0, where do we go? We go back up to R0. So we got to go to Q1, R0. So we make that transition there. What about on input 1? Where would that take us? Q1, R1, because we are in Q0, that takes us to Q1 no matter what. And we're in R1 right now, which has a self loop on 1, so we stay in the R1 column. So we go down like this. Let's do the other 2. So in Q1, R0, the bottom left state, what do we do on input 0? Well, you notice here that the Q states always go between the rows. So because in the original machine, it just goes back and forth no matter what. So no matter what's going to happen, we're going to go up to the Q0 row. So we're in the Q0 row, but it says originally we were in R0, but on input 0, that takes us to R1. So in fact, we go back like this. Yeah, it's kind of annoying to have all of these crisscrossing arrows, but let's do 1. So 1 takes us to Q0 row, to the Q0 row, and R0 stays in R0. So we have the arrow going upward like that. And what do you think the Q1 R1 state's going to do? It's the same idea. So the 0 is going to do a diagonal like it did before. Maybe I'll do a long transition like this. And then the 1 transition is just going to go vertical like the other one. Okay? Any questions on why we're doing that? Because we want to look at each of what the machines would have done before. So let's look at this machine right now. Are there any final states? No. So which ones should be the final states?
Q0 and R0.
Oh, let's see. So we're doing union right here. So if among these 4 states, if it has a Q1 in it, should it be a final state? Why should it be a final state? Because we're doing union of the 2. If either one of the machines is in an accept state, we should be accepting at that point. Because let's just say for Q1, for example, then if we were in either Q1R0 or Q1R1, then the Q machine's in an accept state at that point. So if we're done reading the input then, that means that one of the 2 machines said yes. I don't care about the R machine. As long as the Q machine says yes, we're in the union. So that means that any state involving Q1 in it, that should be a final state. So these 2 states at the bottom are final states. What about that Q0R1 state in the top right? Should that be final too? Yeah, why? Same idea, because R1 was a final state in the original R machine. So I'm going to make that guy a final state too. I'm like Oprah, and you're a final state, and you're a final state. Okay? What if we were doing intersection, like L1 intersect L2? Before that, would any of the transitions or states change? So what is the difference between union and intersection in terms of a DFA? Just the final states. For intersection, which ones would be the final states in this one, in this example?
Just be Q1,
Yeah, Q1R1. Yep, because both of the elements in the tuple, Q1 and R1, are final states in the original 2 machines. Whereas before, it's if one of them is a final state, I don't care about the other one. So the only one for intersection, so maybe I put it in blue. So blue for intersection. Then the only one that would be final is this one in the bottom right. Cool. Any questions on how we did that? Do we know how to do this in general then? Or should we phrase it in a formal way? I think we should phrase it in a formal way. And you might as well know the name of this method. So this is something called the product construction. Because it's taking the product of the states in some sense. And we'll have an actual Cartesian product in a second. But it's called the product construction because you're taking the product of the states. If I had 5 states in the first machine and I had 4 states in the second machine, how many will this method make? How many states? If I had 5 in the first one and 4 in the second one, how many in total? Product. 20. Okay. Because I can be in any one of the 5 states of the original. Independently, I can be in any of the 4 states of the other one. So 5 times 4. Okay, so let's let M1 be a DFA. So I'm going to call it Q1 sigma delta 1 Q01 F1. And I'm going to have a second DFA, which is exactly the same, except it's now 2. So instead of Q1, it's Q2 sigma delta 2 Q02 F2. And I'm going to call them DFAs. Okay, well, we got to make a DFA for the, let's just say union. So let's see. So we will construct a DFA M1, sorry, M equals, so no subscript on this guy. So it's just run-of-the-mill Q sigma delta Q0F as follows. So how did we make the set of states for the example that we did? When we had the Q0, R0, Q1, R1, all that stuff. How did we make those states?
Essentially, we listed all the possible combinations.
All the possible pairs.
That was good.
Okay, so all the possible pairs. Well, as long as the first machine is first in the pair, we're good. So the set of states here is going to be the Cartesian product of the original state sets. So it's just all ordered pairs where the first state comes from the first machine and the second state comes from the second machine. That's why I was saying ordered pairs before, because they're ordered pairs. We're not ordering pairs here, we're we have pairs that are ordered, okay. Let's do the transition function last because it's the most complicated. Let's talk about the start state. So I'm going to ask a question and I'm going to re-ask the question as we're doing more of this. What are states in this machine? Structurally, what are states in this machine? I'll tell you the answer and just make sure to remember because I'm going to ask it again. They're ordered pairs because the state set here is Q1 cross Q2 is Cartesian product, so every state in here is an ordered pair. And then you may think, how, you can't do that. States have names. They can't be ordered pairs. I can name the states however I want to. So I'm just calling the name of a state an ordered pair. It's just the name of the state. It doesn't actually carry any real meaning. It's just the name. So the start state then must be an ordered pair because every state in this machine is an ordered pair. So it must be an ordered pair, meaning it has a state from the first machine and a state from the second machine. Well, how did we find out what was the start state in the machine we made earlier? Right, it's the start states of the original two. Well, the start states of these two, I think, are Q01 and Q02. So I'm going to put those in as the ordered pair. Actually, let's do the transition function next because I want to hit the final states last. Okay. So let's do the transition function. What does the transition function take as input? No. So like the transition function, in order to execute the transition function, what things do you need to provide to it? Almost. So what thing, if I want to execute a transition, what things do I need to know? Yeah.
Like the state and the connector.
Right. So we need to know the state and the character in order to execute the transition. And the transition function then outputs what? Once you know the state and input combo, what does it give to us?
The next state.
The next state. Cool. What are states in this machine? Ordered pairs. You see, I told you I was going to ask you again. So delta of, so the transition function of a state, which is an ordered pair, with an input is what we need to determine. So inside here, we got an ordered pair. I'm going to call it Q1, Q2. With input, let's just call it A. So I'm going to put this in blue to remind us. Q1 from the first machine M1, or I guess a state from M1. Q2 is a state from M2. And the symbol A is in the alphabet. It's just a character, just to remind us what it means. So the transition function outputs a state. What are states in this machine? You probably are guessing how many times more am I going to ask? So it outputs a state, which is an ordered pair. So the result of the function must be an ordered pair. Cool. So now we just got to figure out what's in this ordered pair. Okay, well, let's see. Well, the first coordinate is devoted to which machine? The first machine or the second machine? The first coordinate. The first machine, right. So how do we determine what goes here? So it corresponds to the first machine. Yeah.
It's just some Q in Q1.
It's some state in the first machine. Well, how do we know exactly what's going to happen? Exactly. So we look at the transition function of the first machine. What did the first machine do? We figure out what the first machine's state would have been and then paste it back into here. Well, how do we figure out what that transition function is? Well, we look at the definition of M1 and we see, delta 1 is the transition function for the first machine. So delta 1 of something, but every transition function takes one state and an input. What is the state for the first machine? that we need to feed into here? Q1, exactly. Q1, and what is the character that we need to feed? It's just A. Excellent. And so then what do you think is going to be in the second coordinate? Delta 2 and Q2. Excellent. Any questions on that? Oh, so we're completely done, right? You can tell by my tone I'm not. I'm kidding. So what are we forgetting? Press F in the chat. Okay, so we forgot the final states. But notice something interesting. In these pieces that we've done, did we even think about union or intersection? So this method works up to this point, whether you're doing union or intersection, which is pretty nice. So let's do union for the final states. So what is the structure of final states in a DFA? No, I was careful and not to ask the other question. What is the structure of the final states?
It's a set of states.
It's just a set of states. Cool. So we always have to write a set notation. Now let's get to the question. What are states in this machine? Ordered pairs. So let's call the state name Q1, Q2. And what was our criterion for union of whether this state should be marked as final in the original example?
Q1 is accepted or Q2 is accepted.
Right. So Q1 was an original final state in the first machine, or Q2 was a final state in the second machine. Well, how do we figure out whether Q1 is a final state in the first machine?
See if it exists in F1.
Yeah, if it's in F1, exactly. And then I think for Q2, we just need to check if Q2 is in F2. Excellent. Any questions on that? What if I wanted to do intersection? I must have forgot. I meant to do intersection. We need to do this whole method over again. What needs to change if we wanted to do intersection?
Change the order.
If we change this from an or to an and, we get intersection immediately. Nice. So what can we conclude then about the set of regular languages? Are they closed under union? Yeah, because if we take two arbitrary DFAs, apply this procedure, we get a DFA for the union. What about intersection? Exactly the same. So what we've just shown is that regular languages are closed under union and intersection. In fact, there's another way we could have proved intersection, which you're actually going to, actually we can do it right now. Suppose that we didn't know that trick of just changing the or to an and. Let's just say we forgot that trick. Is there another way we can prove closure under intersection from just union and one other result that we did last time? What are regular languages also closed under? Complement. What if I have union and complement? What could we do? Yeah, your friend and mine, Augustus de Morgan. Okay, what was his law? It says that the intersection of L1 and L2 is the same thing as complementing L1, union the complement of L2, and then the whole thing complement. Well, if we have union and complement, we get intersection because these are equivalent. We can just complement the original two DFAs, do the product construction, and then do another complement once we make the product DFA. So those are two different ways you could have proved intersection. Any other questions about that? Cool. Let's try concatenation, which is the next one on the list. So let's look at a particular string. Let's look at some string in sigma star. And we want to know, let's actually ask this. So if we have two languages, L1 and L2, and we have our string W here, and then we want to determine if W is in the first language concatenated with the second language. Because a DFA would have to do that. It would have to, if it was going to be made for the concatenation here, it would have to determine whether it's a member of this, if we wanted to show that it's closed under concatenation. So what does the concatenation say? Give a high-level description of what that means. What is the concatenation language?
We append every string with the other string from the other language.
Right, so we have every string from L1 concatenated with some other string in L2. So just pick any old string out of L1, pick any old string out of L2, concatenate them together in that order. Okay? So if we wanted to determine if W is a member of L1 and L2, well, that means that there's some split in the W string let's just say that it is this split right here, where so this is the scenario that we want to determine. We want to determine if there's a split of some kind where the first half is in L1 and the second half is in L2. We want to determine if there is a split such that the first piece belongs to the first language and the second piece belongs to the second language. What's the problem here? Or what's the difficulty at least? I don't know what the split is. Could it be conceivable that the first string is empty and the second string is the entire string? It could be. It could be the complete opposite extreme, where the first string is the entire string and the second one is empty. It could be somewhere in the middle. But even more than that, well, could we just say, well, let's run the first machine on the, let's just say we happen to know that there's a split and we know where it is, even though we don't. Here's the problem. If I know where the split is, let's just run the first machine up to where the split is and then continue from the second machine. How do I instantaneously jump to the second machine? That seems problematic, because if I just have a transition from this state in the first machine to the start state of the second one so I can pick up where it left off, that transition has to read something according to DFA rules. Seems difficult, doesn't it? So we're actually going to take a little bit of a detour and then come back to this question. So what we're going to do is we're going to enhance the model of DFAs such that this problem becomes far easier in that model. And then once we have established that, we will show that this more powerful model that can do instantaneous transitions and whatnot, this more powerful model is equivalent to DFAs. And then because of that, we will show through that roundabout way that regular languages are closed under concatenation. Okay? So let's, unless there are questions about this, we can move on to that. Okay, so what are the things that we want? I mean, there are a lot of things we want, but what are the things that we want out of this model? Well, we want to have transitions that don't read anything. That's something that we would want in order to accomplish this problem. Because, as I was saying, we needed to read something if we just wanted to connect the first machine to the second one. But another thing that we're going to allow is that we can have any number of transitions from a state on the same input. So it turns out that this second point, we can allow that into the model, and it doesn't change the fundamental power of the model, what things it could compute. So, so here's the definition. So instead of talking about a deterministic finite automaton, DFA, we're going to talk about something called an NFA, which is a non-deterministic finite automaton. NFA is a DFA, but allows for these two. So the definition's exactly the same. We have a set of states, we have an input alphabet, we have a transition function, we have a start state, we have a set of final states, but here we have transitions that don't read anything, and I'll clarify what that means in a second. And we could have this scenario. We could have a state that has a transition on A and another transition on A. But also, if the character B is in the alphabet, we could not, omit the transition involving B. Whereas the DFA model said you have to have a transition no matter what on every input symbol. Here we're going to allow you to just omit that if you wanted to. Okay, any questions on what the model is? So I need to clarify what this this term really means. So you may think, okay, well, let's suppose that we're at this state right now, and our next character is an A. You may think, okay, well, what transition should we do? Should we do that first one or the second one on A? So I'm going to communicate this in a very clear way, and hopefully you get it, because there are some people, professional people, who do not get it. In fact, I just recently refereed a new book that's being published, and the material was the things from this class, and they got the non-deterministic definition wrong, completely wrong. Okay, so a lot of people get this definition wrong. You see it all over the place on the internet. There's a precise meaning to what the definition is. So what does it mean? So what does non-determinism mean? I guess it's not formal, but it's very precise at least. So non-determinism means the NFA always makes a choice if it will eventually lead to acceptance if such a choice exists. So if we have two choices, one of them is will eventually lead to an accept state and accept the string, and the other one, there's no way that we could accept the string if we took the other route, we will choose the first one. Okay? If we have if every choice that we have cannot possibly lead to accepting the string, it doesn't matter what choice we make. If we have two choices or more that both or more will lead to accepting the string, we'll just choose one of them. But the key here is that the NFA always makes exactly one choice. It will never make 2, 3, 4, whatever number of choices. It always makes exactly one choice. Always. Yeah.
How does it know if it's going to be accepted? Does it have to try everything?
Great question. I don't know the answer either. So this is actually something that's kind of weird about NFAs. So NFAs cannot be built in the physical world. You nod as if it's like okay, cool. So I'll explain what it is first, and then I'll say why we're actually doing this. So what was your question? Sorry, I forgot.
Yeah, how does it know?
How does it know? So it doesn't actually know in the sense that it sees a path ahead or something. It's just you think of it like the NFA has a crystal ball, and it just shakes the crystal ball, and it happens to know you should take this route. So it's like a magical device that will figure out exactly one of the choices to make. Yeah.
Quick question, I guess. If it eventually leads to acceptance, and NA always makes the choice that will lead to acceptance, doesn't mean
If there is one.
If there is one, doesn't that mean that as long as there's multiple paths, as long as it leads to acceptance, it'll be fine.
Yeah, it'll choose one of them.
Just at random. Or
We don't know, but it always chooses one. So the key here is that we're not simulating the NFA. It's just the NFA is running. We will figure out how to simulate it deterministically, like in the real world. How would we simulate it? So you may think, okay, Ryan's gone off the rails. Ryan's crazy. Time to abandon ship. There's still a few hours to drop before Ryan gets too crazy. No. So why would you do this? So in computer science, what we do a lot of the time is if we have a problem that's really, really, really hard to solve with the current models that we're working with, we often try to augment the model in any way that we can so that the problem becomes much easier. And then if we show equivalence to our standard model, where it seems hard to actually do it by hand, but the augmented model is easier, then we would work with that and show equivalence. That's the one reason why we're doing this. Concatenation appears difficult for DFAs to do, but it's really easy for NFAs to do. So let's actually do an example. One more thing before we get to the example is that these transitions that don't read anything, we're going to call them epsilon transitions. Okay? So let's actually do an example. So NFAs, it seems like it's just way too complicated right now. I'm promising you, NFAs will make your life far easier as we are doing more problems. I promise you. I've taught this class 3 times. I know that it gets, the definitions get tricky, but once you start working with non-determinism, it's way easier to do pretty much the rest of the class. So let's actually do an example. So I'm going to make an NFA, and then we can talk about what it actually, the language it recognizes. So let's make a little NFA right here. So this guy doesn't happen to have any epsilon transitions now, but it follows the rules of what NFAs say to do. It has states, it has transitions, and with the Q0 state, we have 2 transitions on 0. For all the other states, we have some missing transitions, and in fact, Q3 has no transitions coming out of it. So let's look at the input 1010. Is it possible for this string to be accepted in this machine? Yeah.
Yes.
Yeah, how?
I mean, so computation.
Or just like, what would the machine do? Or what's a choice that it can make? Yeah.
Q0, Q0, Q0. I mean, Q0 to Q0, Q0 to Q1, Q1
Yep.
to Q2.
In fact, the hand is kind of forced on that one because there's only one transition on input 1, and then for the 0, now we have a choice. So, another professor was watching. So, for the 0, we have 2 choices. It could either stay in Q0 or it can go over to Q1. Should we take the one that stays in Q0? No, because think about what happens. Well, if we did, well then the second 1 that we see, it must stay in Q0. And then for the last 0, it could either be in 0 or 1, but then there's no way to accept. So we must take the one going to Q1, and then the only thing we could do is go to Q2 and then Q3. Do you have an idea about like the set of strings that this thing accepts? Let's make a small change. I'm going to look at the input 1011. Is it possible for this string to be accepted? No. Why?
Because that's the end is zero.
Yeah, because the end is 0, right. So yeah, there's nothing we can really do here. What about...
Oh,
0010?
that's good.
That's also good. See any pattern?
0, 1.
What were you saying? It can't have a 1 at the end, but what else does it need to have?
It just has the end in 0, 1, 0.
Has to end in 010. So all binary strings, W ends in 010. Yeah.
So with the last state that we're in, it's kind of like a dead state because it doesn't have any transitions. So could it just be anything that has 0, 1, 0 in it, or does it have that?
Good question. There's no transitions on Q3. So if we somehow ended up at Q3 and had things left to read, then we can't do anything, which means that the computation will stop and not accept.
Okay.
So I haven't defined computation, and I probably won't for NFAs, but computation always has to read the entire input. If it doesn't read the input and you're in a final state, it doesn't mean anything. It has to read the entire input. Okay, so this is actually really easy compared to a DFA. Well, you have to like figure out, well, what are the last 3 characters that I've seen? And then in the final state, you have to have transitions that go somewhere else. So you have to figure out, okay, what are the last 3 things that I've seen? This is really easy. And another way that you can view this is, look at the start state over here. This says, you just read off a bunch of stuff, and then finish off with 010. So you can think of this as basically just read off the things that are not really important, and then read the things that are important. What if we wanted to change this to not W ends in 010, but 010 is a substring of W. In other words, it just appears in the middle of W.
We would have
Oh, sorry, we're out of time. I'll see you on Friday.